So what I'm going to talk to you about here is how to do virtually everything with UKCA. So what I'll explain is a bit about the unified model. You've been using it for the past few days. I'll talk about how code is developed for it. I'll talk about what I mean by virtually, what I mean by virtually everything, and what I mean by everything. So what is the unified model? It's an atmospheric model, and it's integrating our knowledge of the atmosphere forward in time. It considers lots of different things. We've got surface processes. We consider shortwave radiation, vegetation, clouds, convection, precipitation. And the aim was to kind of reproduce the behavior of hazardous weather systems. And it operates over a range of scales. Operational forecasts might be a few kilometers. If you've got a global scale forecast, say for the seasonal forecast, that would be, tens of kilometers. These are probably slightly smaller numbers now. These are from a couple of years ago. You'd have, the seasonal forecast, 60 kilometers. And then we have kind of climate runs, 100 plus kilometers for, 10, hundreds, thousands of years. And then you might have research mode where you're running very, very high resolution, potentially, down to tens of meters. And it's an old code. It was, it's over 25 years old. We're at version 12.2 is the latest one, but it goes all the way back to the 1990s, I think. And it's designed to run, as I say, across this range of scales. And so you might have climate runs at 300 kilometers, and you might have these runs here at 300 meters. And the point is that all of these, the same schemes are supposed to work in all of these. You're supposed to have this kind of seamless prediction across all these scales, which is a tricky thing to maintain. More recently, there have been developments for using the to simulate exoplanets, which is really exciting, really interesting. And it's also a really good test of the model. So, the unified model is supposed to be just solving, fundamental equations of the Earth. It's not, it's not specific to the Earth necessarily, other than the forcing files that are used, the orography. If you specify it for another planet, it should also reproduce the behavior of that planet. And of course, we're starting to be able to observe exoplanets more and be able to kind of compare output to those observations. So I think this is a really interesting avenue of work. And of course, in terms of climate models, there's been an increasing number of complexity of processes represented in climate models over time. So if we think about, the climate models starting off in the 70s, they were rather simple by today's standards. The bars here, the height of these bars is representing the complexity of the processes that are simulated, and we're adding in more and more processes each time. So the most recent, the fifth assessment report, well, it isn't the most recent actually. This is a bit of an older graphic. Started to have atmospheric chemistry, and it's even more atmospheric chemistry for the most recent assessment. And what we do in Cambridge, which is where I'm based, we work on a part of the called UKCA, which you've all been using for the past week, and we develop new schemes. So Scott gave an excellent talk yesterday on how a new scheme was developed and implemented in the model. And we're interested in kind of chemistry climate interactions. We usually include between 75 species, which are in StratTrop that you've been using, to the 240 species, transported species that Scott was talking about yesterday. There'll be hundreds of reactions, and we need to try and accurately simulate the changes to these gases, because we want to think about their impacts back on the main model through radiative feedbacks. And it's quite important to get these gases correct. So this is some work that was done a few years ago now, looking at what happens, if we have a run without atmospheric chemistry, what ozone field do we use, and how does this affect our results? So if we have a kind of pre-industrial control simulation here with interactive ozone, and then we run a kind of standard climate change experiment. This is a 4x CO2 experiment. With this interactive ozone, we get this particular answer here. And if we rerun this experiment using an ozone climatology derived from this pre-industrial control, we get a different answer, and we get quite a big difference in these answers. But if we were to specify the ozone generated from this blue run, we get a curve that much more closely follows this original simulation. So this is the reason why for stuff like UKCA, we really want to ensure that stratospheric chemistry is included to make sure that we're able to kind of accurately simulate changes in ozone under climate change. In terms of developing code for the unified model, this is kind of what you've been doing over the past week. There's actually around 900,000 lines of code. It's mainly in Fortran 2003, and there's around 200 active developers of the model, mainly at the Met Office. It uses rows, which you've all become very familiar with, and silk, which is that kind of window that pops up and shows you what the job is doing as it runs. Code is held in something called Subversion repositories. So you might be familiar with something like Git. Subversion is a slightly older version control system. But actually there's a wrapper around it, which is called FCM, which is where all those FCM commands you've been using come from. This stands for Flexible Configuration Management. And so the majority of the development work is done by the Met Office, but there's also development work done outside, so we work with UKCA and also work on convection and other developments. And in terms of the development process, it's basically what you've been doing this week. You make a ticket and you check out a branch from the trunk. You develop your code changes. That's kind of the step you've been doing here. If you were going to say take this change and put it back into the trunk, so say you think Alice and Bob are really important, this should be included in the next Earth system model, you need to get it back in. This is where things like making a ticket actually become really important. This is where the documentation goes for your change. This is how the code is assessed. There's a kind of testing process, which I'll talk about in a moment. It's not just running the model like you've been doing here. There's actually standard tests that kind of test a lot of things for you automatically. And these help you when you undergo this kind of review process to commit code back to the trunk. And there were 3 releases a year. We've just had one a few weeks ago to release 12.2. And there'll be another one in about 4 months' time for the 12.3 release. And this is just for code changes. These aren't necessarily for kind of science configuration changes in the rows suites where you might change some numbers. These are for making new code for the trunk. And the reason why the release cycle is so frequent is because the is an operational model. And for operational requirements, you need to make sure that the code is rigorously checked and you're sure that it's of a high standard. So this coding process, testing process is to ensure that. There's a similar process with slightly longer timescales for science improvements. So if you ever think about making a change for UKSM2, you'd be doing a similar process with a ticket, but there you might not be making any code changes. What you'd be doing potentially is tweaking numbers in panels, in rows, to kind of get the right settings, potentially turning things off and on. You might turn on a new scheme that's been implemented previously in a code change. In fact, the way the think about this is actually much more complicated. I'm not going to go into this in any great detail, but you can view this on the track pages. And as you can see, it's much more complex than the graphic I had previously. So for science changes, so the change you're making here would be thought of as a science change. It's a new improvement. You've got Alice and Bob included. From the perspective of testing, you'd need to make a long simulation. You'd want to run. Typically, we run for 20 years in what's called an AMIP configuration, which is where we run with prescribed sea surface temperatures and sea ice fields. And that might take 2 or 3 weeks to run. And then the output from that run can be passed through some standard assessment tools. And these produce, lots of different plots compared against standard metrics. And it allows people to kind of look at this run and say, how good is this run compared to the previous run? Have we improved something? Have we reduced a bias? Have we included a new process that's important and interesting to consider? There's an additional set of tests that you can do as well. This is you're done using what's called the row stem utility. And this compares against things called known good output. So this isn't to say that the output is correct. This is to say that we have some output from the model that we think is the best that we've got at the moment, and we want to check against that output. It also runs some other tests, which I'll discuss in a moment. And so on the HPC system, so the big computers, we might run a 2-day UKCA job. It takes 7 minutes to run on 144 cores, and it needs about 112 gigs of memory to run. And the important thing when making a code change is you need to show that your change works when it's turned on. So Alice and Bob, work. You've got their diagnostics to show that the flux is going. You're depositing them, and it doesn't break anything when it's turned off. So if you've managed to put a change on a switch, if you don't include it, you haven't changed the answers from the way the job was previously. It might be slightly different if you've got a bug fix. You found an error somewhere and you're changing it, then you might change answers. But for a science change, generally you want to put it in with it turned off and check that the results don't change. So at 12.2, there are 328 different testing jobs, and 33 of these are UKCA. So that means that if you wanted to test, your single branch of that you've been working on, if you test it completely, that you can go away and automatically test against 328 different configurations and check that it doesn't break any one of these. And these different configurations have been decided on, to be included in this test suite because they might be important ones to do with weather forecast or climate runs, that sort of thing, or testing particular configurations that are important for future work. On the big supercomputers, it tests with numbers of different compilers, and it also tests on smaller Linux systems, a bit similar to the virtual machine that you're running on, again with different compilers. So it's important to check against different compilers, because you might have one compiler. We're using the GNU compiler for this this training because it compiles quite quickly. But it might, you might allow a code change through that compiler. It doesn't flag an error, but you might find the Intel compiler says, actually, I think there's something wrong with this change you've got here. And that just helps with the robustness of the code. It also tests restart file creation tests. So that's the recon task that you've been seeing. It also tests for coding standards, the metadata, say, that you've been adding, as well as other things like boundary conditions and stuff like that. As well as testing against this known good output, it checks, in terms of restarting the code, in terms of running with different parallelization options, so using OpenMP or not. So are we running with multiple threads? Processor decomposition. So you're running a job that runs on 1x2 processors. So it's got one processor east to west and two processors north to south. But you might run it 2 processors east to west to 1 processor north to south, for instance, on this system. But when you run on the bigger HPC, you might be 16x8 or 12x8, something like that. And it also tests a range of different optimization levels. So generally for climate runs, we run with what's called a safe optimization, which is where it runs quickly, but not too quickly, because we don't want it to break the code. Generally, higher optimizations will change the answers, but mean the code runs faster. So in very high optimizations, the compiler will do a bit of work for you, make the code run even faster, but that has the risk of maybe changing the answers out when you do that from a safe run. You can also run with a debug option. This allows you to kind of maybe find errors in the code better. And then a rigorous test will kind of do lots of checks, which slow the run down, but allow you to see, well, okay, I've got an array issue here. I'm trying to access an element that doesn't exist, that sort of thing. And in this testing process, if you break KGO, so if you change the answers, you need to explain why you've changed the answers. And it might be that it changes the answers. That's perfectly fine. Your code is supposed to change answers. It's a bug fix, something like that. And these tests protect the code and the scientific configurations from being broken by another change. If you haven't got, you've made a really interesting bit of science that's gone in, you put Alice and Bob in, but you don't test that in a row stem test. Someone else might come in and accidentally remove it. And this is a problem, because then you have to add it back in again. If you put it in as a row stem test, it means that the person accidentally breaking it has to ensure it doesn't get broken. We could think about these row stem tests in this way. So this is a kind of graph of how the jobs work. You can actually view a graph similar to this in your jobs if you change the view from a kind of dot view to a kind of blobby view. It starts off with a recompile. It will then go through to a reconfiguration task. This is the kind of very basic level that you're essentially running today. And then it will run the atmosphere. So that's what you're doing in your jobs at the moment. And what it can then do is go away and test against known answers. with which have been saved somewhere else. This is this KGO comparison, and it will test the restart file hasn't changed when your change, and it will test the atmosphere output hasn't changed with your change. When you change the different compiler optimizations, you often get different answers here, and that's expected and perfectly fine. You can also test if you change the numbers of processors that you run on. So instead of running 1 by 2, you run 2 by 1, for instance. And you should get the same answer. You know, the model shouldn't give a different answer unless there's particular settings that allow you to maybe change the answers there. But you, generally speaking, you want it to give the same answer. And what you do then is, rather than compare against KGO, you might compare both runs and see, you know, okay, we run 1 by 2 here and 2 by 1 here, do we get the same answer if we do that? If we run with different numbers of threads, so we might run on 2 threads compared to 1 thread, again, you shouldn't change the answers, and we can compare these and see, you know, whether we're getting the same answers or not. And as I say, you shouldn't change KGO when you change the numbers of threads. You might test kind of restarting. So, you know, as I say, in the row stem test, we run a 2-day job. You're running a 3-hour job here, but a 2-day job, you can break it up into 2 1-day jobs. And again, you shouldn't change answers. You shouldn't have a different answer if you do it in day 1 as one job and day 2 as another job, compared to days 1 and 2 in a single job. So you can run all these different tests, and the way row stem is configured, it will go away and run all those tests for you. So this is a kind of massively blown up view compared to what you've been running. You'll have been seeing essentially this view on the left, but you can view it in this kind of blob view here, which is what this looks like here. And you can see all these different blobs. This is the graph that I showed on the previous pages, going through, and you know, the greens here means it's running, the lighter green means it's been queuing, and the gray means it's completed. And the reason the Met Office can kind of run all these jobs so quickly is they have got a very their infrastructure is dedicated to kind of running the It's designed around essentially running this one model very well in lots of different configurations. We have the Science Repository Service you've all been using. It has the code and the suites set for it, and it has the mirror the Met Office have. So if Mozzers goes down, you can still run these jobs. Everybody has their own little virtual desktop that they're running, so similar to the virtual machine that you have here. They can run on these Linux servers, and everything runs through Silk server. So the Silk server you have is the virtual machine you're running on, but at the Met Office, they've got dedicated servers that send these to either the Linux systems or these HPC systems. And for the long jobs, everything gets sent to this mass archive. These are very big and powerful computers. You know, when this computer, the XCS, was first installed, it was number 11 fastest in the world at the time. It's dropped down a bit. This is the number from last year, but it's still very powerful. And then this doesn't include the new computers that have come in since I made this graphic, which will be even more powerful again. But, you know, most people here don't work for the Met Office or have access to those systems. You know, what if you don't have access to that infrastructure? You know, if you're a university student or a researcher at a UK university or abroad, you know, you should be able to get access to the source code. You've all got access to source code at the moment. You know, you might be able to get HPC resources. You know, in the UK, we have Archer 2 or Monsoon 2 if you have a Met Office collaboration. You might be able to get access to an analysis platform, so Jasmine, but, you know, these aren't at the same site. You know, you've got issues with data transfer, that sort of thing. It's not as seamlessly connected as at the Met Office. And access to row stem and the internal tools, you know, could be limited or might not be available at all. You know, Archer 2 technically has row stem, but it's not really it doesn't really work properly. It's kind of used to install the model and that's it. Monsoon 2 does have it, but there are problems running it. So what do I mean by virtually? I mean, you could probably guess that I mean by a virtual machine. You know, we're all using virtual machines this week. And the Met Office developed or built on top of an existing tool that was built for Joules, for FEM rows and Silk, to allow running the on it, and you can use it in your own PCs at home or servers if you have access, and you can run VirtualBox and Vagrant on them, or you can use AWS as we've been using this week. And all the files for this are available on GitHub. I also ran this training on Jasmine last year in a slightly different way, but it's possible to run this system on the cloud, and it means that you then don't have to have access to HPC to run it. I think it's very useful for the and for UKCA. You know, it's good for developing and testing code changes. It has a much faster turnaround time. If you've had any experience with running on HPC, you'll see that actually the compile step is 2 or 3 minutes. It might take 7, 8, 9, 10 minutes at least, if not 20 minutes or more on something like Archer 2 or the Met Office machines, with only 10 minutes to compile from scratch and a few seconds to recompile. Also, these standard jobs you're running, they take a few minutes on 2 cores. They're quite small and nice and easy to use. And of course, it can be used for training, which is what we're doing this week. Now, before it ran, we had to set these jobs up to run on the virtual machine, and Mohit was actually really helpful in doing this at the time. The virtual machine needs around 3 gigs of memory to run at a minimum in terms of the operating system that's there. And I thought that we wanted to run UKCA on this. The biggest issue would be the memory requirement. I wanted to have a system that you could run on, somebody's laptop rather than having to run it on a supercomputer. And the reason for the memory issues is UKCA has a lot of extra 3D fields, all the different tracers that you're adding in for the aerosol and for the chemistry, and having to save additional forcing fields and stuff like that. And it needs a lot of further temporary arrays at runtime, as well as the diagnostics. As I said earlier, you need over 100 gigs of memory for a climate resolution run, which is 192 by 144 by 85 grid points. But on the virtual machine, they'd been having very small jobs that were running. These only took about 1.5 gigs of memory to run. So this is a job that was running on the virtual machine when I picked it up. It runs for 27 time steps, which is 9 model hours. And it doesn't have UKCA turned on. In fact, it doesn't even have any aerosol in it at all, I think. And so it ran in about 8 minutes, which was pretty good. But if I took a suite that Mohit provided, of the same resolution, N48 L70, this took over 12 gigs of memory to run, and it took over half an hour to run in a 1x1. It took slightly quicker, 15-20 minutes for 1x2. But that's quite a long to run, and the memory requirement is too much. You wouldn't be able to dedicate that much to a virtual machine on a laptop. But there's tricks we can play to make this better. We can reduce the number of vertical levels. So this reduced it down to about 7.5 gigs. We went from an L70 to an L38. We could turn off basically all the stash output that was there. This reduced the memory a little bit by about 0.5 gig. So if you look in the stash output of your job, there's actually a rather limited set that's there. That's kind of just there for minimal testing purposes. But the main issue we've got is this kind of big peak right at the start. That's where all this memory is coming from, really. And it was a bit tricky to track down, but eventually I realized this was due to a simulator package for clouds. And we don't need that for this job. It was turned on originally in that suite. Turning it off brings it down to about 4 gig for the suite. So actually this is the suite that you're running effectively in the training. And this is why it can run on this virtual machine. We've got this job. It only takes 4 gigs of memory to run. You need about 2 to 3 gigs for the operating system. So you can run on a 6 to 8 gig memory machine, which is what you have here for the training event. The sacrifices we've made, though, we've had to go from climate resolution. So this is what UKSM 1 uses, down to a VM suitable resolution. We've halved the number of grid points and reduced the vertical levels down. So we've cut it off in the stratosphere. We're at 40-kilometer top, and it's very blocky in terms of the resolution. So I wouldn't recommend using these jobs for science at all. Although when I started in Cambridge 15 years ago, this resolution was what we were using for science, because that's what we could run on the HPCs at the time. So it's interesting to see how times have changed. What do I mean by virtually everything? I'd got this job running, but actually it only ran for 1 hour, 1 model hour. What was happening is on the next time step, I was getting an error occurring. And this is an error that you might end up seeing in your work with UKCA and with the It's an error in a particular routine called by CG stab. And the interesting thing about this error is it's known that the errors aren't here. There isn't an error in this routine. There's even the error message when it comes out. It says this is a common point for the model to fail. It's not here. There's a nan or an infinity somewhere else. You're doing something wrong somewhere else. Don't look here for the problem. And I did some debugging, and it looked like actually there was a UKCA routine. This is Azad hetero, and this allows chemistry and aerosol to couple together. And so somehow there was a nan appearing in this routine, and I didn't quite know why. This suite ran, this configure, the code ran perfectly well on other compilers on other systems. Why was it failing on the virtual machine? And I think one thing important to know about the UM, and people may, if you know Fortran, you may have spotted this. Mostly the UM doesn't explicitly declare that its numbers are what's called double precision, which is where you use 64-bit numbers to save your information, which is usually quite important for scientific codes like this. You want to have that accuracy in the numbers that you're storing. We might have some codes might declare it as kind equals 8. You might use something like selected real kind instead, but whatever happens, double precision is usually you've got to have a kind parameter. What the UM uses, and this is purely for historical reasons, I tried to get to the bottom of this once, and it's purely because at one time, early on in UM development, it was decided to use compiler flags to do this. So you won't have really interacted with compiler flags in this course. Essentially, they are options you can pass to the compiler to say, do certain things with my code to make it better or faster or check for things. And one of those things you can do is say, make sure all my real numbers are double precision. So if you're using the Intel compiler, you'd use this flag. If you're using the Cray compiler, you'd use this flag. And what the UM had for the GNU compiler was this flag. They're all slightly different. They all should do the same thing or a slightly different thing. One thing it is important to note is that sometimes in the code, there is an explicit declaration of double precision when you're setting a variable. So you might say that 1.0 is different from 1.0 D0 because the D0 here means I want a double precision 1, if you like. And these still existed in the code at the time. And so there is a Fortran intrinsic called tiny, and what this gives you is the smallest possible number you can represent in the precision you're on. And if you have a tiny of double precision, it should give you the same between these two things if we're using the compiler flags correctly. And this is kind of the smallest number you can represent before any smaller number is effectively 0, which is a really, really tiny number. UKCA concentrations are like 10 to the minus 15, something like that when they're really small. These are, orders of magnitude smaller again. So you wouldn't think this should be a problem. But what we find with the GNU compiler we're using on the virtual machine is when you use this flag with tiny, it gives you what's called a quad precision tiny. So not a double precision, a quadruple precision tiny. So it's even smaller again. And this means that if you use tiny anywhere with this double precision number, you're basically saying 0. And if we were using tiny as a convergence test to make sure we were close to a small number, but effectively we were never reaching this small number. This small number was 0, which meant it never converged. We got nans in the code and the code was breaking. So how do we fix this? Well, what we can do is we can put another compiler flag in for GNU, which basically says double precision numbers are 8-bit, are kind equals 8. So now we have the same answers on both of these things. This then means that the code could run. In terms of what we mean by everything, so these compiler flag changes went into the trunk at 10.7, and I put row stem testing jobs. So the configuration you're running for the training, that's also using a row stem job on the Met Office system, and it's part of the developer group, which is used when all changes are made. So hopefully UKCA is protected for any change that goes into the UM, as well as the UKCA specific groups. And then I said, you know the answer to this story now, basically. What if we could use the virtual machine for training? So this would mean everybody has their own dedicated computer. This is what you have. You've all got your own little machines that you're running on. It's a simpler setup. You haven't got these complicated multiple settings, that you might have, post-processing, archiving, that sort of thing. It's got 3 steps: make, reconfiguration, and atmosphere. And also, you can do this training, you can play around with UKCA without having to run on a computer like Archer or Monsoon. You can try before you buy when it comes to UKCA. You can try it out, see if you like UKCA. If you think it's something that you could use, you could then look into running on a supercomputer later. You don't have to have that access first, which can be quite a barrier to people trying to get started with the model. And this certainly was beforehand. So, you go through the tutorial tasks. You've been doing this week. We make our emissions data set up to N48. This then allows us to see Alice and Bob. Once we have the reaction in, we can look at the diagnostic fluxes through these reactions, look at the dry deposition that was coming out. And then in tutorial 10, you'll be looking at what this does to the aerosol optical depth. This is, this to a certain extent, this is great. Also, you can do this without, outside of this training event. If you wanted to refresh yourself, you can boot up a virtual machine and take a look at things again. All your suites and your branches are saved back on Mozzers, and you can reconstitute quite easily. So in terms of conclusions, testing environments as well as production environments, these help you develop code changes in a timely manner. And this virtual machine environment developed by the Met Office, this allows people to run their own version of the UM. The standard tests, these row stem tests that I talked about, these have actually been implemented on the virtual machine. So you can run row stem on your branch, or you can play around with row stem on your branches and see how it works, have a bit of an understanding of the testing process. And it can certainly be very helpful if you're doing some changes to run row stem. It can be quicker, and it gives you kind of, have I changed the answers? That sort of thing is really useful to know. What it does do as well is it means there's this standard system that a non-Met Office person can use to implement and test changes, prior to running on a HPC. What you can do in terms of your workflow, you might have access to Archer 2 or Monsoon 2. And what you'll find is that the throughput on those machines can be quite slow. It's perfectly fine if you're running, a 20-year AMIP job. You don't really mind about the fact that it might be queuing for an hour or two before it then runs the next job step. But if you're having to develop some code, you're putting in your Alice and Bob traces, you're doing some sort of science change where it's going to fail the first time you do it. There will be a mistake somewhere in the Fortran code or how it's applied when it runs. Having the ability to have the throughput increased on a virtual machine. So you've got this small testing job, you can implement your changes on that small testing job, check that it compiles under the GNU compiler, check that it runs, and then you should be able to go and say, well, I know that my code compiles now. I haven't got to debug that on Archer 2, where it might take an hour to compile it due to the running in the shared queue. I don't have to wait for hours for it to run, because it will run instantly on the virtual machine. So you can speed up that time to science by running it in the virtual machine. And then what you can do is you've got your code debugged. You can then pick up a standard job, UKSM job, for instance, on Archer 2, implement your branch. You might need to regrid your emissions to the right resolution if you're changing something like that. But essentially, you're then good to go running on the HPC. You might have a little bit of debugging to do potentially, but it's much faster. I mean, when I started 15 years ago, you might get 1 or 2 compiles a day out of the system we had at the time. It was very slow and painful to debug. Now you can get through 1 or 2 compiles in 10, 15 minutes, and it can be really helpful to kind of speed up making your code changes. If you want to know any further information about this, we actually wrote this up a few years ago, and developments have been made since to port it to AWS. Also, standard suites are provided at different versions, and it's pretty easy to make a new one up. You can just upgrade the suite you have to the new version, UM version. It should just instantly apply the changes and allow you to run it. So that's all I have from this. So thanks very much for listening, and thanks for being patient given that the previous speaker wasn't able to attend. Are there any questions? I'll stop sharing so that I can see see those.
Hey, Luke, thanks for the really interesting talk. So a question regarding this virtual machine, these procedures or application, how much does that regularly cost? For example, if one wants to use the virtual machine to do such kind of testing stuff. And second one is, how difficult is it to set it up?
So in terms of how much it costs, if you have a server or a PC that you can run it on, you're allowed to install VirtualBox on, then it's essentially the cost of the computer, or it's free if you've already got an existing computer, if you like, because VirtualBox, Vagrant, and the script files for the virtual machine are all open source. So that's free at the point of use, essentially, once you've got everything set up. In terms of if you were to run it on AWS, that gets a bit more complicated, dependent on the instance type that you're running on. So unfortunately, the virtual machine isn't small enough to fit on what's called the free tier types, which is where you don't have to pay. You're all running on what's called a T2.large instance, which is 2 cores and 8 gigs of memory. Off the top of my head, I can't quite remember what the cost of that is, but it's not vastly expensive. You might be talking $10 to $20, potentially to run for quite a reasonable amount of time. I think the total cost of this course for 20 people to have 20 virtual machines up and running for essentially 7 days will be around $600 or $700 for the whole week, and that's where they're running continually, overnight. And of course, what you can do is turn it off when you don't need it. So actually, you save a lot of money by doing that. You can run on faster instances as well. So I could have given everybody a slightly beefier instance, and that would have cost a bit more, but for the point of this course, it probably wouldn't have given anybody any additional benefit. But essentially, if you wanted to do that, you could run on a slightly bigger one with slightly more cores or more memory. So often I have to check that the code still works on the virtual machine every new release. And what I will do is run on a bigger one that maybe has 16 cores or something like that, and 48 gigs of memory, something like that. And I can run more jobs at the same time. So you're running one job at once because that's all the resources you have. But if you want to run multiple jobs at once, you can make a bigger instance. And as Courtney mentioned, you can resize these on the fly. So you can make a small one, make it bigger, do what you need, make it smaller, that sort of thing. In terms of setting it up, it's very easy to do that. You basically go to the GitHub site, the Matomi VMS GitHub site, which is linked, I think, from the tutorial pages. Clone that repo, and you would just type Vagrant up. You make a few edits, type Vagrant up. If you've got VirtualBox installed, that's what you're using. It will take about an hour to build the virtual machine. And then you would type Vagrant SSH and you go into it. Similarly with AWS, it's exactly the same. You would just put -- provider equals AWS, and it will then build it on AWS, for instance. And you've got there's instructions on what you need to kind of tweak to get that to work. I'm hoping over the next year to try and get it working with VMware, potentially, also maybe other cloud providers as well, if I can get access to those, to try and make it more accessible. But it should be possible. I mean, the problem with VirtualBox is often it's a security concern for some institutions because it technically gives you root access. It could give you root access to the file system of the machine it's running on. So Cambridge doesn't mind, we're in our group in Cambridge where they're happy for us to have root access. But in the Met Office, for instance, they can't run the virtual machine on their normal systems. They have to run it on what's called a dirty laptop, which doesn't have access to the rest of the infrastructure. So that, in that sense, you get more capability of running outside the Met Office than internally at the moment. I do have a branch that should allow it to run on Azure, for instance, but I haven't been able to test that for a bit as well.
Okay,
so did that cover
that's
everything?
Clear. That's wonderful. Yes, that's wonderful. Thank you.
Great. Any other questions, Luke?
Yeah, hi Luke. You said you ran this course on Jasmine last year, and I was just wondering if you could share your experiences of running on a VM versus Jasmine, and perhaps tell those who don't know what Jasmine is, because I think it's a shared data and compute resource, isn't it?
Well, actually, I was using the Jasmine unmanaged cloud. So rather than running it on the Jasmine compute systems, I was running on the Jasmine unmanaged cloud. And in fact, I can, here's one I prepared earlier in terms of this. So if everybody can see that. So the way it worked on Jasmine was a little bit different. So I couldn't use Vagrant to run on Jasmine. I used Ansible. So a guy called Richard Smith at Cedar was very, very helpful in kind of initially porting the Vagrant scripts over to Ansible, which I then took over. The way you're running on AWS is you're all running on a copy of an Amazon machine image that I made. So I essentially, and in fact I used Ansible for this as well, I made up an image of the virtual machine. I installed the UM on it. I configured it to allow it to run. I installed a kind of all the jobs and the tutorial information on there. I powered the machine down and I made a copy of that as a machine image. And then when I made all the virtual machines for everybody here, what I did was just say, give me 20 virtual machines using this image. And a script went away, made 20 virtual machines, and gave, and I could just get the IP addresses. And so what the emails I sent around to people are, this is the IP address of your machine. This is the SSH key file that you need to connect to it. Everybody has their own IP address. And in fact, I think you and other people have seen, if there's a problem with your virtual machine, I can make another one almost instantly. I can go in and say, give me another one. This one's not working, which sometimes happens. It's not quite the same with Jasmine. So Jasmine doesn't allow you to make these virtual machine images. It has a couple of fixed ones, I think a CentOS and an Ubuntu image. It also it doesn't allow me to kind of tweak stuff like the size of the image. So I think you've all got 35 gigs of disk space. I couldn't do that with the image on Jasmine. It only has, I think, 8 gigs of disk space. And so I needed to then do things a bit more cleverly. Also, Jasmine only gives me a single IP address. So for each of you, you've got your own unique IP addresses. That's the same throughout the week. For Jasmine, I have a single IP address, which is the same all the time. But what that means is that I either had to make a single virtual machine that was really large that everybody accessed, and then I'd have to think about, user management and stuff like that. What I ended up doing was kind of faking running on this unmanaged cloud. So what I did is I had a login server, which has the IP address. This is the public facing IP address. And then I made, 20 virtual machines with private IP addresses that were accessible from the login server. I then had to have an NFS server, which mounted this volume where I'd installed the UM. So this is where I'd gone through and I'd run, I'd installed the UM, I'd put all the tutorial documentation, everything like that was installed on this volume. Each of these student VMs then mounted this volume read-only, and then it's symbolically linked within the home directory umdir to the umdir on this volume installation. So I kind of faked a UM install. Also, when the VMs are built, they're not built from this image. They have to be built from scratch. So it has to install all the packages for each one. So it's not, it doesn't take a second or two. It takes an hour to run each of these. You can run it in parallel. So you can with Ansible, you can say, go away and give me 20 VMs, and it will go away and do that. And in fact, you can see on GitHub, I have this repository here where it gives all the scripts I used for that. Occasionally, I might have a VM that doesn't work properly, and I had to work out how to identify that and then rebuild that VM, and it was a little frustrating. But actually, it all worked perfectly fine. From my perspective, AWS was easier because I could do this machine image and I could boot it up, but it still worked in either sense. But it's a bit more involved to run it on Jasmine using the unmanaged cloud. You can do a lot of stuff with the unmanaged cloud. There's lots of interesting stuff with kind of Jupyter notebooks and stuff like that people have done as well, and other things. And I think there's a Jasmine seminar series where you can see how people have used Jasmine. I didn't try running on the kind of the managed Jasmine system. You might have access to that for kind of data analysis, and you can certainly access the mass archive from Jasmine to access some jobs from there. But I didn't try and run the UM on that system. It was purely on the unmanaged part. And in fact, this is how it looked exactly the same as you're running here. It's the same system essentially.
Yeah, that's great. Thank you very much.
Any other questions?
Question. Yeah.
So somebody speaking?
Yeah, me.
Hi. Yeah.
Yeah. I want to know. Sorry, I want to know. Sorry.
Yeah.
I want to know. The VM just used for training or normal normal user.
So, I mean, anybody can get access to it. And in terms of doing the training, you know, you could set it up yourself and run the training yourself, you know, just reading through the web pages and doing the tasks. As I said, you can use it. I mean, primarily, I would think of it as a kind of training and a kind of development and testing platform. So you don't need to do your development on a big HPC. You don't need to do your testing on a big HPC. What you do need to do, though, really is do your science runs on a big HPC. I think the VM probably isn't suitable for doing science configurations, running science configurations, because the testing suites that are there are quite small. You know, the biggest job that I've run is this N48 L70 job. So it does have a stratosphere, but it's still, again, very low resolution job. You could conceivably go away and make an instance which had enough RAM to run, you know, these 112 gig jobs, and you gave it enough cores to run these big jobs. And, you know, if you were to, I think I did this calculation when I got the AWS access. If I were to run a job like that, you know, I wanted to run UKSM1, for instance, on AWS, and I was able to install it correctly. To get the whole of the UKSM, to get the whole of an instance for a year, so constantly having it on, was something like £100,000 of cost, or maybe $100,000. And generally, when you're running, you know, if you get access to a central HPC resource, that cost is kind of hidden. You don't have to pay for that explicitly. So something like AWS is great for smaller things where you can turn it on and off. For big jobs, you have to be very careful about only using it when it's turned on. You know, you have to be much more managed as to what you're doing with it. But it might be possible. I have not tried to do that. I've never had enough resource to do that. And my focus has been on kind of facilitating people using the model, facilitating science and the speeds to getting to doing the science. But certainly you can use it for development. And I think James, you might be able to comment on this, used it a lot for developing CryStrat2, or may have used it for CryStrat2 development. So it has its place, but probably not in a science sense.